Performing experiments is hard, but only if you don't know how to go about doing it. Here's a step-by-step guide to do any experiment. Every physics experiment starts with a question that guides the investigation. We got to identify what physical relationship we're testing and why. Here's an example. How does the length of a pendulum affect the time it takes to complete one full swing? This part kind of describes the physics principles that form the basis of this experiment. It basically shows us the equations, variables, and expected relationships according to an established theory. According to a simple pendulum theory, the period t is related to the length L by the equation t equals 2 pi square root of L by g, where g is the acceleration due to gravity. A hypothesis is a clear, testable statement about what you expect to happen based on theory. This creates a direction for us to work in. An example is if the length of the pendulum increases, the period will increase proportionally to the square root of the length. Now we can finally start the fun part. We gather all the materials needed to conduct the experiment. The accuracy depends on the proper selection and calibration of the equipment that we select. An example is the string, a small metal bob, ruler or meter stick, a stopwatch, protractor, and a stable support stand. The setup explains how the experiment is arranged and how variables will be controlled or measured. Example, we attach the string and bob to a fixed point, measure the pendulum length, and pull it slightly to one side. Now we can finally take our data. First, we have to take careful and repeated measurements to ensure accuracy and reliability. Example, we measure the time for 10 complete swings at different string lengths. Divide by 10 to find the average period, and record each measurement precisely. This is an optional step which quantifies uncertainties and potential errors in measurement. Example, timing errors due to human reaction time, inaccuracies in measuring length, and small variations in swing amplitude can cause error. Now it's time to use our math. The collected data is now analyzed to find relationships and verify whether they match theoretical expectations. Example, plot period t squared versus length. A straight line indicates that t squared is directly proportional to L. This confirms our theoretical model. Here, we can summarize what the data shows and discuss whether the hypothesis is supported. Example, the graph shows a clear linear relationship between t squared and L, confirming that the pendulum's period increases with the square root of its length. Finally, the main findings are present and we reflect on what was learned from the experiment. Example, the experiment verified that the period of a simple pendulum depends on its length, consistent with the theoretical prediction. The result also demonstrates how gravitational acceleration affects oscillatory motion. Here, documentation ensures that others can replicate your experiment and verify your findings. Example, record the pendulum length, timing data, environmental conditions, and calculation steps, and there you guys go. A universal guide for any physics experiment you want to conduct. Thanks for watching.